All right, so chapter five is a chapter on what's known as discrete probability distributions. In chapter 3, we talked mostly about the statistics portion of probability and statistics. In chapter 4, we mostly talked about the probability portion of probability and statistics. Chapter 5 and also chapter 6 will kind of combine probability and statistics together when we talk about probability distributions. So when we're talking about variables in this particular section, keep in mind that a statistical experiment or observation is any process by which measurements are obtained. Like if we were counting eggs in a nest or measuring daily rainfall and things of that nature. So we use the letter X to represent the quantitative result of an experiment or observation. And we call X a variable. Just like we call X an unknown in a math equation, we're using X to represent an unknown quantitative result of an experiment or an observation. Now, when it comes to random variables, a quantitative variable is a random variable if the value that X has in an experiment or an observation is given by chance or a random outcome, hence the word random variable. Now, there's two different types of random variables. There's discrete random variables and there's continuous random variables. A discrete random variable can take on only a finite number of values or a countable number of values, whereas a continuous random variable can take on any of the countless number of values in a line interval. So a way that I like to describe it is the difference between discrete and continuous variables is similar to the difference between a whole number and a real number. So every whole number is a real number, but not every real number is a whole number. Like even if you just look at whole numbers, right? You have your counting numbers, 1, 2, 3, 4, 5, so on and so forth. And you have 0, and you have the negative numbers, -1, -2, -3, -4. Just looking at the interval between 0 and 1 itself, there are an uncountable number of values that lie just between 0 and 1. So that's kind of what the difference between discrete and continuous random variable are. When we describe a discrete random variable, it's usually the result of a count. Like, for example, number of students in a math class, right? We describe people, we describe objects for the most part using whole numbers, whereas a continuous random variable is the result of a measurement on a continuous scale, meaning that it can be expressed as a decimal. So both discrete and continuous random variables can be expressed using whole numbers. But the difference is if it can be expressed as a decimal, it cannot be discrete. It has to be random. It has to be a continuous. So for example, measuring the time it takes a student selected at random to register for the fall term. What are we measuring? Time. Can time be expressed as a decimal? Yes, that is a continuous random variable. Counting the number of bad checks drawn on upright bank on a day selected at random. What are we measuring? The number of bad checks. Checks are whole. They usually don't write half a check. So we can only describe it using whole numbers. So this is a discrete variable. Measure the amount of gasoline needed to drive your car 200 miles. What are we measuring? Amount of gasoline. So anytime that we fill up our car with gas, we see two numbers. We see the price of how much we're paying for the gas and how much gas we're putting in. Both of those are expressed as decimals. So this example is a continuous random variable. Picking a random sample of 50 registered voters in a district and finding the number who voted in the last county election. What are we measuring? The number of voters, number of people. That is a discrete random variable. Now, regardless of whether your variable is discrete or continuous, it will have what's called a probability distribution. So a probability distribution is an assignment of probabilities to each distinct value of a discrete random variable or to each interval of values of a continuous random variable. So no matter what type of random variable you have, it will always have an assignment of probabilities to it. So each value of that variable will have a probability attached to it. Now, because we're talking about probability, we still have to remember some key things from probabilities that will still apply. Now, first things first, the probability distribution must have a probability assigned to each distinct numerical value of the random variable, whether it's discrete or continuous. But because we're talking about probabilities, again, each probability has to be between 0 and 1, just like we talked about in chapter 4. And then when I add up all the probabilities together, I must get a value of 1. Again, going back to chapter 4, the sum of all probabilities of an event must be 1. Same thing with probability distribution. So here's an example. In a Pew Research Center poll, subjects were asked if the use of marijuana should be made legal, and the results from that poll have been used to create the table below. Does this table describe a probability distribution? Well, let's go back to the questions that we were asked before. Does each distinct value of the variable have a probability assigned to it? Are each probability between 0 and 1? And when I add up all those probabilities, do I get a value of 1? Well, let's find out. Well, here are my responses. Now, if you wanted to be a little bit more technical with it, you could assign a numerical value to these responses. So if my response is, let's say that's the variable that I'm measuring, we'll let 1 be yes, 2 be 3, 1 be yes, 2 be no, and unsure be 3. Now, the question is, does each of these values of x, does each of these responses have a probability assigned to it? Yes, they do. Are each of these probabilities between 0 and 1? Yes, they are. When I add up all these probabilities, do I get a value of 1? Well, let's find out. 0.41 plus 0.52, that's 0.93. Add 0.07, I do get a value of 0.1. I get a value of 1. So yes, this table does describe a probability distribution. What about this one? Senior executives were asked when job applicants should discuss salary, and the table below is based on their responses. Does the table describe a probability distribution? Well, here's the value of x. Here are all the potential values of x. Does each value of x have a probability attached to it? Yes, they do. Are each of these probabilities between 0 and 1? Yes, they are. If I add up all these probabilities together, do I get a value of 1? 0.3 plus 0.26, that's 0.56. Plus 0.1 is 0.66. I do not get a value of 1. Therefore, this is not a probability distribution. Here's another example. A tool of cryptanalysis is to use relative frequencies of occurrences of letters to break codes. In addition to cryptanalysis, creation of word games also uses the technique. Oxford Dictionaries did an analysis of letter frequencies in words listed in the main entries of the concise Oxford Dictionary. Suppose Langley took a random sample of 1,000 words occurring in crossword puzzles. The table on the following slide shows the relative frequency of letters occurring in the sample. So here is the frequency of letters in a 1,000-letter sample. It looks like we have some probabilities that are missing. Well, why don't we go ahead and fill in those probabilities? So when we talk about probabilities here moving forward, we're kind of treating them the same as we would relative frequency, meaning that we take the frequency of each value of the variable and we divide it by the total. Well, what's my total? My total here is 1,000. So for each frequency that I'm missing, I'm going to divide that frequency by 1,000, and that will give me my probability. So for example, letter A, if my frequency is 85, my probability is 85 divided by 1,000, which is 0.085. I'm going to do the same thing with the other 5. 112, that's 0.112. For I, it's 0.075. For 72, that is 0.072. And for 36, that's 0.036. Okay. Now, in the previous slide, do the probabilities of all individual letters add up to 1? Well, that's how we're going to know if we have a probability distribution, because we have every potential value of the variable that we're measuring. So there are only 26 letters of the alphabet. So if you wanted to be more technical, you could assign a numerical value from 1 to 26 for all these letters. But regardless, let's move on. Each letter has a probability attached to it. Each probability is between 0 and 1. But now we have to see if we add these up that we get a value of 1. So what I'm going to do is I'm going to add up this column, I'm going to add up this column, and if the sum of both of those columns is 1, then we're good. So we're going to start with the first column here, 0.085, 0.021, 0.045, plus 0.034, plus 0.112, plus 0.018, plus 0.025, plus 0.030, plus 0.075, plus 0.002, plus 0.011, plus 0.055, plus 0.030, and total of the first column is 0.543. Now, in order for this to be a probability distribution, both columns have to add up to give me 1. This means that the sum of column 2 has to be 0.457. If I don't get 0.457, it's not a probability distribution. So let's see what we got here for column 2. 0.066, 0.072, 0.032, plus 0.002, plus 0.076, plus 0.057, plus 0.069, plus 0.036, plus 0.010, plus 0.013, plus 0.003, plus 0.018, plus 0.003. And I do end up with a value of 0.457. So this does, in fact, represent a probability distribution. Okay. Now, if a letter is selected at random from a crossword puzzle, what is the probability that the letter will be a vowel? So that means I'm selecting one value at random, which means that I'm looking for the probability that I either get an A or an E or an I or an O or a U. Now, the good thing is I'm picking one letter, and one letter cannot be another letter at the same time. So these events are mutually exclusive. So that means since I'm doing OR probabilities, I just add the individual probabilities together. P of A plus P of B, plus P of E plus P of I plus P of O plus P of U. And since we've already calculated those probabilities, we'll just add them all up. 0.085 plus 0.112 plus 0.075 plus 0.072 plus 0.036. And I get a value of 0.38 as my probability. Now, with probability, a probability can be thought of as a relative frequency distribution based on a very large sample size. Now, this will mean that it does have a mean and a variance and a standard deviation. And we kind of talked about this before when we did variance and standard deviation. So when you have a population probability distribution, you have the Greek letter mu for the mean and the Greek letter sigma for standard deviation. For a sample probability distribution, you have X bar for the mean and a lowercase s for standard deviation. For this particular chapter, we're going to focus on population probability distribution. Specifically, we're going to talk about discrete population probability distribution. Okay, and so the mean of a discrete population probability distribution is given as the sum of all products of X times its probability. So we're multiplying each value of X by its respective probability. We're adding up all those products. The mean is also called the expected value of X. Anytime that I talk about the mean of a discrete population probability distribution, I'm talking about expected value and vice versa. And then we also have the standard deviation. So standard deviation of a discrete population probability distribution is going to be similar to how we did standard deviation in the past in chapter 3. There are going to be some differences, which I'll explain, but for the most part, it's roughly the same. You have your mean, you take X minus the mean, square it, but then this time we'll multiply that by the respective probability of that frequency. Then we add all those up, and then we take the square root to find our standard deviation. Okay? So again, x is the value of that variable, p of x is the probability, and the capital Greek letter sigma means a sum. Now, the mean of a probability distribution is often called expected value. I just mentioned that. It's because it represents a central point or a cluster point for the entire distribution, whereas the standard deviation is often represented as a measure of risk. And that just has to do with the size of your standard deviation. Remember, when we talked about standard deviation in chapter 3, we said that the larger your standard deviation is, the more spread out your data is at the center. The smaller your standard deviation is, the more close together the data is at the center. So it's a similar concept here when we talk about a measure of risk. A larger standard deviation implies a greater likelihood that the random variable is going to be different from its expected value. And vice versa for a smaller standard deviation. A smaller standard deviation implies a greater likelihood that the random variable will be similar to the expected value. But now let's talk about how to calculate that. So calculating the mean, calculating the expected value is very simple. First, you have to identify the random variable and all its potential values. Then you need to find the probability for each value of x. Remember, that's relative frequency. We just talked about that. So once you have your values of your variable, once you have their probabilities, you're going to multiply each value of x with its corresponding probability. You do that for each value of x. Then you add up all those results. The resulting is your expected value. When we calculate standard deviation, the first few steps are the same because, one, you still have to identify the random variable and all its potential values. You still have to calculate the probability for every value of x, but you also have to calculate the average. So you do the exact same thing that you did to find the expected value for step 3. But here's where we start to find standard deviation. And again, some of this is going to be similar to what we did in chapter 3. Subtract the average, subtract the mean from every value of x. So x minus the mean. Then we're going to square x minus the mean for each one. Once we do that, then we multiply each result by its respective probability. And then we add up those results. Now, when we add up those results, that's where we get our variance. That's just like when we did variance and standard deviation in chapter 3, the second to last step always gave us the variance. And to find the standard deviation, you just got to take the square root of the variance. And that's your standard deviation. Okay? Let's put that into practice. At a carnival, you play $2 to play a coin flipping game with 3 coins. You flip 3 coins in one round, and you win $1 for every coin that lands on tails. Are your expected earnings equal to the cost to play? So in this game, the random variable of interest counts the number of tails in that show. What is the sample space for the values of this random variable? So first off, we need to identify what our variable is, what we're trying to measure. And we need to identify the probability. But in order to find the probability, we need the sample space. Well, there are 8 equally likely outcomes for throwing 3 coins. First, you could have all 3 being heads. That's this right here. You could have 2 of the 3 coins showing heads and 1 coin showing tails. That's these 3 guys right here. You could also have 2 tails and 1 head. That's this, as well as this. And then, of course, you could have all 3 coins showing tails. Tails, tails, tails. So there's my sample space. There's my sample space. There are 8 equally likely outcomes. I can use that information to find the probability for each value of that variable. Well, here's the value of the variable. We're looking for the number of, we'll call this tails. Number of tails. Either I could have 0 tails, I could have 1 tail, 2 tails, or 3 tails. Well, remember, here's our sample space. Here's our sample space. H, 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 HT, HTH, THT, THH, HTT, THT, and TTH, and then TTT. So I have 1 instance of having 0 tails, 3 instances of having 3 tails, 3 instances of having 2 tails, and 1 instance of having 3 tails. So once again, find the probability. We find our relative frequency. We take each frequency and divide it by our total, which is 8. So for 0, 1 divided by 8, that's 0.125. 3 divided by 8, that's 0.375. And since this also has the same frequency, it's going to have the same probability, 0.375. And then for 3, 1 divided by 8, again, that's 0.125. If you want to double check that, add those up to see if you get 1, you should be fine. Now comes the next step where we, multiply each value of x by its probability. So 0 times this is 0, because anything times 0 is 0. 1 times anything is itself, so this will be 0.375. 2 times 0.375, that's 0.750. And then 3 times 0.125, that's 0.375. So to find our average, we take that entire column, we add everything up. And this actually gives me a total of 150 as my expected value. The expected value is that sum 150. Are you expected earnings less than, equal to, or more than the cost of the game? So the problem says it costs us $2 to win the game. We're expected to get $1.50 back. That's an expected net loss of 50 cents. So the expected earnings are less than the cost to play the game. And all games of chance are like that. Whether it's coin flip, whether it's dice rolls, whether it's poker, a lot of these, that's how, casinos use expected values to help control the house earnings. Okay. Let's go a little bit further and let's calculate expected value. Variance and standard deviation. So I'm going to take this off. Remember, our expected value is 150. So here's x, which means I'm going to need x minus the mean, and x minus the mean squared. All right, so in my calculator, in the y equals portion, I'm going to type in x minus 150, because that was the mean. And I'm also going to do x minus 150 squared. If you wanted to save yourself some time, you only need that second part, x minus 150 squared. So I'm going to go ahead and graph all of these. So I have x minus the mean. And then I have x minus the mean squared. Okay, so we start at 0. So I have negative 1.5, negative 0.5, positive 0.5, and positive 1.5. All right, then I'm going to square all those values. 225, 0.25, 0.25, 225. So now I'm going to take all of those values and I'm going to multiply each of these values by the respective probability. Remember, this was 0.375. This was 0.125. So I'm going to keep the decimal places as is because I want to make sure I'm as accurate as possible. So I'm going to take x minus the mean squared times the probability. So our first one, 225 times 0.125. So 225 times 0.125. That's 0.28125. Next one, 0.25 times 0.375. And they're actually going to have, since these two are the same and these two are the same, it's going to have the same value here, 0.9375. I'm sorry, 0.9375. 0.9375. 0.9375. And then our last one, 225 times 0.125. And I think I'm going to get the same value as the first one. 0.28125. So now my second to last step that will give me the variance is I'm going to add all of these up. So I got my 2.28125s and I got my 2.09375s. And I get a variance value of 0.75. To find the standard deviation, I'm just going to take the square root of that number. And I'll round that to 3 decimal places. So I get 0.866 is my standard deviation. So my mean was 150, my variance was 75, my standard deviation was 0.866. Now, what does a discrete probability distribution tell us? Well, first off, it helps us give the complete sample space on which the distribution is based, because we need the sample space to find all those probabilities. Then there's a corresponding probability of each event in the sample space, right? That's part of the requirements in order to have a probability distribution. And then of course the formulas that we were given tell us how to find the expected value and the standard deviation of that distribution. Now, linear functions of a random variable. So if I have a random variable and if I make any changes to that random variable, then I can express that as a linear function of x. Right, where the new random variable is now L, and I have A and B be constants that help change the variable. It's very similar to a linear function on a graph, right? Y equals mx plus b. It's very similar. But because I'm changing the variable, I'm also changing the mean, the variance, and the standard deviation. Now, as long as I know what A and B are, and what my variance, mean, and standard deviation of my previous variable was, my original variable, I can find the mean, variance, and standard deviation of a linear function. So for my average, I just substitute the average into my linear function. For my variance, I take b squared times the variance of my original variable. And then, of course, I would take the square root of that number to find the standard deviation. So, and then there's also a linear combination. So let's say I combine two random variables here, x1 and x2. Now, these variables would be considered independent if any event involving the first variable by itself is dependent of any event involving the second one. That's just to establish that these random variables are independent. Now, if I combine them in such a way, or in any such a way, I also get a new random variable, w, given as ax1 plus bx2. That's called a linear combination of x1 and x2. And just like linear function, it also has its own mean, variance, and standard deviation. So here is the mean, variance, and standard deviation. So just like linear functions, they're very similar, right? If I'm taking the mean of my linear combination, I just substitute each individual mean into x1 and x2. For the variance, it's the variable squared that's attached to x1 plus the variable squared attached to x2. So a squared times the variance of the first variable plus b squared times the variance of the second variable. And then, of course, you take the square root of that to find the standard deviation. So let's look at an example. Norm and Gary are entered in a local golf tournament. Both have played the local course many times. Their scores are random variables with the following means and standard deviation. So here's Norm's values. His average is 115, and his standard deviation is 12. Gary's average is 100, and his standard deviation is 8. In the tournament, Norm and Gary are not playing together, and we will assume their scores vary independently of each other. So this is just to establish that we're going to use the formulas from linear function and linear combination in the previous slides. So again, here are their scores here. Here are the formulas here. The difference between their scores is W equals x1 minus x2. Compute the mean, variance, and standard deviation for the random variable W. So here is, remember, here is the form for a linear combination. W equals x1 plus x2. Well, this is not so much different from this. we can make a good assumption that our value of A is 1. And in order to have x plus 1 or x plus x2 be equal to x1 minus x2, my B has to be negative 1. So the very first step is you want to make sure you find out what your A and B are. Once you find out what your A and B are, it's going to help you with the rest of the formula because we're already given expected value and standard deviation of both these guys. Okay? So let's go ahead, let's start with the average. So A times the first mean plus B times the second mean. So that's 1 times 115 plus negative 1 times 100. So that's 115 minus 100, that's 15. All right, now for the variance, we're not given the variance, but because we're given the standard deviation, we can find the variance by squaring both standard deviations. So standard deviation 1 squared is 144. Standard deviation 2 squared is 64. So variance 1 is 144. Variance 2 is 64. So, and also A squared is 1. B squared will also be 1. So I have 1 times 144 plus 1 times 64. That's 144 plus 64, which is 208. And of course, to find the standard deviation, I'm going to take the square root of 208. I'm going to round that to 3 decimal places. Square root of 208. That's 14.422. So as long as you know how to use the formulas and find your A and B, you can work these types of problems. Oops. Last example. The average of their scores is 0.5x1 plus 0.5x2. So we're going to work this pretty much the exact same way that we did the last one. But this time our A and B are going to be different. So our A is going to be 0.5. Our B is also going to be 0.5, which means that A squared and B squared are going to be 0.25. And of course, we have the same variance and standard deviation. So this is going to be 144. This is going to be 64. So let's go ahead and let's find our new average of the average. So that's A, so 0.5 times 115 plus 0.5 times 100. Go ahead and type that in. So 0.5 times 115 plus 0.5 times 100. I get 107.5. All right, now for my variance, that's 0.25 times 144 plus 0.25 times 64. 0.25 times 144 plus 0.25 times 64. I get a grand total of 52. I'm going to take the square root of that variance, round to 3 decimal places. I get 7.211 as my standard deviation. So again, as long as you can find your A and your B and know how to square them, and as long as you can find the variance, you'll be able to work these types of problems because the mean and standard deviation are already given to you. And the formulas here are already given to you. And on the Math Excel, they will also be given to you.